everybody. Welcome back. So let's start with our next session. Great. Okay, so we're going to have a session on latent and thermochemical energy storage. I would like to welcome you again back, and I would like to welcome also our online participants. They are 60, I believe, so quite impressive. So the format is going to be very similar like before, but now we're going to discuss a latent and thermochemical topic with our 4 experts from the field. I would like to welcome all of you and thank you for being here. We're going to also use the presentation opportunity to reflect a little bit on how far have we come as a community and also as individual experts. And then we will have a panel discussion mostly focused on what should we do now, how should we shape the future of latent and thermochemical energy storage together as a community again or individually in the next 10 years, let's say. So, I mean, before we were talking about seasonal or sensible and with a focus on seasonal. Now we're going to talk about 2 new technologies. Maybe not all of you know exactly the details about how these technologies work, but you are, I mean, the main point or one of the main points is that now we're talking about compact thermal energy storage, higher energy densities, and that we're talking about less mature technologies. So in the last 10 years, in both of these fields of latent and thermochemical, we had very big advances, either in the way of commercialization or or scientific advances that we will be able to see in our presentations. So yes, I hope that we all leave this session having very concrete ideas about what we want to do next. So before we go to the presentations, I would like to introduce our speakers. So first of all, I would like to introduce Elena Navarro, and with a special thank you because you jumped in spontaneously. Maybe some of you were expecting a big Canadian guy here, but but Dominic Grew had an emergency and he couldn't join. So we're very, very happy and grateful and excited to have you here. Thank you very much. So a few words about Elena. So she studied advanced chemistry and material science in University of Barcelona, where she did also her PhD in ceramics and high temperature applications. In 2014, she moved to Birmingham, University of Birmingham, to the group of Yulong Ding, where you are currently working as a scientific researcher or researcher, yes, on the topics of material development of both latent and thermochemical energy storage. Thank you, Elena. So next, I would like to introduce Alexis Servault from Sintef Energy in Norway. So Alexis studied mechanical engineering and he did a PhD on oxy-fuel combustion, laser diagnostics, and CO2 capture in NTNU. In 2012, he joined Sintef Energy, where he's now serving as a research manager of the energy storage team with a focus on thermal energy storage and specifically on phase change materials. Then I would like to welcome Andrew Bissell, who is he's the CEO of, I would dare to say, world leading company on the latent heat storage, Sanamp. Many of you have probably heard about it. So Andrew has a background in computer science from the University of Edinburgh, but I guess you can say your heart was in entrepreneurship. So you founded different companies in different fields, in my understanding. And what is the most relevant for this session is that in 2005, you founded Sanamp, where you're also serving as a CEO at the moment, commercializing latent heat storage solutions. And finally, from Eindhoven, Henk Houning. So Henk studied molecular science and had a PhD in physical chemistry. In 2005, he moved to Eindhoven University, where in 2018, he became associate professor. And he is a group leader studying the physical chemistry of thermochemical materials, focusing specifically on improving thermal conductivity, stability, and kinetics. So we are ready to start with the presentation. So I would like to invite Elena first, who will talk to us about advancing the scale-up of high temperature thermal energy storage. Or maybe we can also, should I point there? I don't know actually. I would say maybe it's not.
Okay, so good morning, good morning. Today, so I'm going to try to give an overview of past, present, and future of thermal energy storage, but focusing in energy-intensive industries, so how we can move forward and help that industry to decarbonize. So from my background in high-temperature ceramics, so I tried to use that knowledge that I gathered during my PhD and the experience on working with industry, so how we could help them just to tackle the challenges on their energy use. So one of the things that they mentioned, that they keep constantly saying that industrial space is really expensive, okay? And another thing that during their, when they have designed the process, they have limited space to adapt to any other technologies inside the site. So that made me move forward to look for more compact energy storage systems and how I could deploy them there. So in the past, what I saw, the main challenges on latent heat and also in thermochemical, because after I wanted even more compact thermal energy storage. So the main challenges were, as it was mentioned before, cost, CapEx, and that's still an issue. So we need materials that compete with existing technologies. And in case of latent energy storage, one of the main issues or the challenges at that time, it was chemical stability, segregation, subcooling, volume change. So in these aspects, it has been done a huge effort, and some of the materials are now being commercialized, so they will show you later. And in case of thermochemical, still lower TRL, but it's the main challenge is it's the materials conversion, so cyclability, that's due to agglomeration, mechanical stability. So that was in the past. Here you can see in this graph how the number of publications has dramatically increased. So the first line is when I started my PhD. The second one is kind of when I finish it. And currently the number of publications has increased a lot. What I've seen that the share of thermochemical, latent, and sensible thermal energy storage, it's still in under the same proportion in the number of publications. So that the other day that I was preparing the slides shocked me a little bit. So we're still, I assume that's because of different development stage of these technologies. So the present. So what we are doing in the Birmingham Center for Energy Storage, this is one thing that I'm really involved. It's how we can move from lab scale to industry, which are the challenges. So here this is an example of a foundry industry. I have to say that I've been visiting in the UK and they still work in a very traditional way. So there's waste heat everywhere. They still heat needs everywhere, and they are not connecting those dots. And in some cases, like in this steel industry, they have waste that we saw as an opportunity to use it in the thermal energy storage material. So the idea is how we can, from this, I think 13 millimeter pellet, move to tons of material to store the heat and reuse it later. So we had the design for this specific application in this SME. And then we face one of the first challenges is the manufacturing process. So we have our material in our lab that comes from really pure raw materials, specific particle size. And then we had to move to tons of material who can provide that. So here we talk about critical materials. Prices need to be stable. Is the material that we are using competing with other applications? And we had to, that take us months, reformulate the material because of the scaling up of the grinding, milling, pressing, sintering. So all of that was challenging. But we managed to have CPCMs. In this specific case, we use molten salts, and we design a cascade system. So this is another challenge. So how we are going to fill the material inside the tank, and then how we are going to move it into the site. This one was done outside the company, this piping and connection. And at the end, that's the prototype. That this one, it's around, I think, 1 ton of material. And so that we have come through a path that help us to understand which are the main challenges that we are going to face when we want to deploy this technology in industry. And for the future, so here everyone knows, or you have here, that we want full electrification. We want 100% renewables. And in that case, heat, it's a huge contribution to that pie. And thermal energy storage is going to play a huge role, or we need to make it play a huge role because of its benefits. So you have always seen the challenges of these technologies, but I have to say, I want to highlight that in general, thermal energy storage is kind of decentralized systems that is going to cause a disruption on the current energy networks. So still there are lack of policies for heating and cooling that is going to help us to implement or speed up this change in the process. Also, I have to say that thermal energy storage can work in a wide temperature range, so from minus to 1000 plus degrees Celsius. But this advantage and these opportunities also makes really application oriented. So we need to foresee thermal energy storage in a more compact way, modular way, so we can apply in temperature ranges. And that will help us just to slightly modify designs to apply in different industries. And the needs, so my vision on how this, or how we could help here, the research community and companies, how we could help thermal energy storage to be deployed, is just to maybe stop thinking a little bit on top-down and bottom-up approach. So materials from one side, system from one side, design components in one side, and manufacturing in this case, and how we can, in a multidisciplinary approach, speed up the thermal energy storage development, because we need to have ready this technology, and we need to think about all the contributions from other fields, not just, in my case, not just materials, so what it's needed. So I think that's maybe a little bit more than 5 minutes, but sorry about that. So, and looking for the question and the discussion. So thank you.
Thank you very much, Elena. Okay, so now we will continue with Alexis, who will talk to us about the importance of demonstrating new thermal energy storage technologies under application conditions.
Yeah, thank you everyone for joining this session. And so yeah, it's all about demonstration, right? We heard this earlier pilots demonstration. So therefore the title is about this in office buildings. And you see a bit in the background there behind me, the pilot itself. But why do we do that? What is the real motivation? Why do we, get up in the morning and do that? We all know like these reasons: electrification, growth in fluctuating energy sources, so more intermittent renewable energies and so on, more grid constraints. Some people cannot develop the industry they want on the side they want because they don't have access to enough power. It could be also that the thermal loads are increasing. We see more and more call for cooling loads, and the world will just come to increase beyond the need for heating. So how do we solve that? most people would go for the cheapest and the most available solutions. But as researcher, our role there is to look at these two aspects, of course, but also to make sure we have a sustainable solution for that. And I think that's what really drives us, at least in this development, how to come up with cheap and available, but also sustainable solutions so that we don't put more renewable energy to have a storage solution that is not renewable behind it and another problem for the future. So I think that's really what drives us. And in that respect, we came up to that big box in a building. It's a zero emission building. So we wanted to go with the philosophy of the zero emission storage too. It's not exactly zero emission storage, but we are converging towards that. And we used 3 tons of bio-based wax PCM melting at 37 degrees. And it fitted quite well with the low temperature heating system that they have in that building. And that provides about 200 kilowatt hour of heat storage capacity. And if we were to put a hot water tank, that would have used 4 times more volume. So it would be a very large tank that either you put outside and you have a lot of heat losses, or you don't have space in a zero emission building. Each square meter costs a lot in terms of CO2 footprint. So that was really important there. But then we combine it with a heat pump, with a district heating to charge, and we can discharge it back to the heat pump on the return temperature to support it in case of high demand of heating. And we can also discharge directly to the building, so as a heat source for the building where we don't run the heat pump then. So it's a way to relieve the power grid, for example, when there is a high need for heating, a peak need for the whole city, then at least this building doesn't add to this load. So in that way, we do peak shaving that relieves a lot the local network. It's been running for about 16 months now, so we got a lot of data about it. And I'm not going to go into details, but I have a few publications. So we have learned a lot also how to make the next iteration even better, even more effective, more compact, cheaper. So it's been quite interesting. And not least, the control of that type of unit, how you make it dynamic, how you use it as much as possible, to make as many cycles a year as possible. That's how you decrease the payback time. So that's how you go back to this eventually low capex and low operation cost and so on and so on. And this we have been working quite hard on it. So we are now implementing the model in the building. But that type of control is applicable also to the industry, and it's a very hot topic. Maybe some of you already work on that, but this is what makes the difference somehow. You have the hardware, but when you come to the software, you really help with these two combined to have a low payback time, so short return of investment. So that's how you get the business case going. And just to give a bit of a timeline, this was a big milestone for us, but first, we started to test in the lab. You see on the very left, we have the same technology, but there we tested with CO2 as a fluid, so compressed CO2, and we used it for cold storage for industrial applications. And then we realized that this could be used also with water in a building. So that's what we demonstrated there. But the second step that I described before, it's really operational condition. It's not really a lab anymore. It's really a building, and that's where we started to really pass the threshold somehow. We got a lot of people interested in the topic, and when people come to this room and the stuff is as high as them, it's like 3 tons of PCM, it's a kind of big machine, and we put it in a technical room that is really big, so they can really come into it, turn around and see, and they see it's working. It's been there for a while, so they feel a lot more confidence into the technology. So that's been very useful. And from that on, we have a few cases that we want to demonstrate, some in buildings, but also some in the industry. The industry players are a little bit more flexible, let's say, when it comes to the development loop and testing new pilots and so on. So it's very important for us to go through that. So we're going to implement that. It's going to be bigger than the first box, of course. And our goal behind it is to upscale production, decrease cost, and so on, and reach a much larger, let's say, public for this kind of technology. So we have this spin-off company, Cartesian, that will be established later this year. And now that we do that, we also know that the tech can also work for high temperature, a little bit higher temperature at least. So we also work in parallel loops in R&D projects to make sure it's working on a wide range of temperature. But the goal is to have a flexible tech that would work with different temperature ranges there. So typically -50 to 150 degrees is what we target with that. So we are focused very much onto a single loop with a lot of applications behind, but I think that's how we managed to enter quick in that field, because we haven't been in that field for very, very long. but fortunately, we will stay for very, very long. Yeah, that was me. Thank you.
Thank you. So now we continue with Andrew, who is going to talk to us about his dream of making advanced thermal energy storage the new normal.
Perfect. Thank you. So when we started, we took on what we thought was quite a big challenge. I mean, we weren't really part of the thermal energy storage community at the beginning. We were just some people with a problem, right? The problem was how do I make my house and the houses of all the other people work in the most autarkic way they possibly can? And right at the beginning, I thought that would all be about electricity. Okay, which shows how much I knew, nothing. And then I read my electricity bill and my gas bill, and I thought about, kilowatt hours instead of pounds and pence, and arrived at a conclusion, which I know you all know, which is in a residential home, it's about 80% thermal and 20% electrical. And that was a complete revelation. If you look at the world final energy consumption stats from the International Energy Agency, you see that, on a global basis, it's 46% heating and cooling and 18% electricity. And yet in popular culture, it's all about electricity. Right. So that pushed us in the direction of saying we will solve something important in thermal. And actually, at the beginning, we also wanted to do interseasonal storage. And we came to the conclusion that it couldn't be economically done, and we couldn't fit it into buildings if we were doing it at individual buildings. I see from the presentations earlier that it can be economically done if you're doing it in the district heating network against an energy from waste plant, but you can't do it at individual buildings, I think, yet. So we took on the challenge of displacing the combi boiler, the gas combi boiler. And we said, what's going to displace it will probably be heat pumps. We started with solar thermal. We rapidly transitioned to heat pumps in our minds. And what will be the dominating problem will be that people have got used to a really small box. And they need a small box again. They can't be expected to take their combi boiler out and replace it with a big hot water tank. So we targeted ourselves with the smallest possible box. And we thought about all the technologies, right? Not just phase change materials, hot bricks, and so on. And we came to the conclusion that what you all have in front of you in the little hand warmers that are, kindly being put on everybody's place here. I'm sorry for the people online. You'll have to imagine them. But that, in a sense, had the secret. All we had to do was stabilize the phase change material in those, sodium acetate trihydrate, make it work reliably, 10,000 plus cycles, make a box that would actually turn that into something that could directly replace a hot water cylinder, do it with extreme energy efficiency, A+ energy rating, and be heat pump compatible. And if we did all of that, we could help enable the transition. And that's what we set out to do. And I'm not going to go through everything here, but I am going to say that, like in so many fields, the people who look like they're pioneers are actually standing on the shoulders of pioneers who went before them. And in our case, we go back to Maria Telkes in the 1940s in Massachusetts, making the first interseasonal, actually, solar thermal house, in the sense that they had it was a storage that was recharged by solar thermal that could actually last for up to 10 days to deal with troughs in solar generation. And that would have broken out into the world and become huge if the chemistry had been stable. And so what we discovered was very early in thinking about this, that we needed a chemistry partner that we could reliably work with. And we worked with Professor Colin Pullum, maybe you can stand up for a second, and Dr. David Oliver at the University of Edinburgh. And from there, we were able to perfect our chemistry. And that got us into the ability to then move the technology forwards with Dr. Maurizio Zaglio over here. And, we were able to actually make this work tangibly. And then we moved from there to how do we ramp this in the market? And that's all about raising money and deployment and sales and doing all the things which I think in a way fall in the socio-political, which is why I've put that green badge on, and I'm going to the socio-political section later. It's about persuading people. is in a way about giving them permission to buy the thing that they actually want to buy because they know they want to make a difference. And some of that permission is about making it low cost. And we've got into a range where we can compete with existing solutions. And that's really important with a box. And you can see that in the exhibition, which is about 4 times smaller than the hot water tank that it replaces. Again, that 4 times number that comes up. And in the next 10 years, we've deployed in the last 10 years about 20,000 heat batteries. So it's quite a big number for this industry so far, but we're not really very satisfied with that. We want to be into making millions of heat batteries because that's what it takes to move the world. And to do that, we'll do it in partnership. We already signed up a lot of OEMs and distributors. We will partner all over the world in multiple different ways. And in many cases, we'll partner with people in this room, right? Because we're not going to invent every technology that we need, and we're not going to have every solution in our own hands. And we would be very delighted to work with anybody and everybody in partnership. Yeah, we see the same requirements, wide temperature ranges. We see the same requirements for industrial. We see the same requirements for cooling. We have some brands lined up for that. Permafrost for cooling, Central Bank for large scale formats, which we haven't built yet. And in fact, maybe we'll build some of these with people here. But our SunAmp Thermino product today is already breaking open the market in a serious way. And we're really pleased to be doing that. We all collectively need to do something very important. We need to educate, train, and disseminate to the gas industry. We need to give them the tools to willingly transition to something that isn't gas. It's too easy for them today. It's too easy to just go and buy a combi boiler or something like that and stick it on the wall. We need to give them the easy path or the educated path to do something different. And I would make that a challenge for everyone. Thanks.
Thank you, Andrew. And last but not least, Henk will talk to us about the importance of knowledge transfer between science and application, specifically in the field of thermochemical storage.
I hope I don't disappoint you. I'm a bad prophet, not very good in prophecy. I'm also not very good in calculating CapEx, unfortunately. So what I have to offer you is a personal journey in thermochemical materials. But I think the journey has a bit of, aspects which also trigger, the discussion in the field. And that's what I want to do. So when I started 10 years ago, more or less, when also this workshop started, there were 2 figures which were basically inspiring me. I had this graph with, let's say, a household, typically in the Netherlands, where there is enough power, let's say, coming in from some whatever sources in summer, and more or less to transfer that to the winter. And the other thing was the enormous amount of low temperature waste heat. So that was in my background. Now, so I'm now involved, and that's what I show you here in the first, let's say, demos. 2 types of demos, basically one demonstration for really a device, but also a demonstration of industrial scale materials that was already mentioned, which is not really an easy thing. I noticed, and I'm a stupid physicist, of course, so I really had to learn a lot. So for me, I think one of the key lessons was, okay, I know that we have this energy transition and that compact materials for long-term storage could play an important role. I know that we need stable materials for that, and I know that we need fundamental understanding, and there I could play my own role. However, I had to learn that I should embed myself, and that's why I'm also here, in this whole technology chain or knowledge chain, because they put the real questions to me, which are let's say, physical questions. Where are we? Or where are, I try to bring in figures. So if you think about thermochemicals, the main advantage is that you can store heat, let's say, for a very long time, simply because you separate 2 compounds. That's the major advantage. The other advantage could be, but I say could be, is the energy density. However, if you see what is then promised often, it's really on the material level. In reality, you have to go to a system and you dilute that quite something. Here you see the figures. Very important is the fit on the use conditions. I think we now know how to do this for the built environment, but it's very inflexible because it's strongly rooted in basically in the phase diagrams of the materials. So still a challenge. And then maybe one of the other things, cyclic stability. It was also mentioned already for the PCMs. That's still also for thermochemical materials a very important thing. Right. Few examples to illustrate that a bit. I was involved in a project. Oh, no, I ruined. Oh, now it should work again. I was involved in a project which was working, let's say, with vacuum systems, fuel water vapor. What is nice? Okay, it's passive transport. You don't have to do a lot. But what is then the problem? And that is a challenge. Heat getting out of that. So you have an intimate contact between a heat exchanger and a material, which causes a lot of problems and a lot of challenges there. Other example from an atmospheric system here, also working towards demonstration right now. What is there the major problem? Not so much the heat exchanger. What is here the problem is get the flow through the material. So cyclic stability becomes even more critical. And then finally, on the material level, which is basically my own job generally, I think we understand now how to, let's say, play with power, reaction kinetics. What I still see as a major thing is the stability, because if you improve stability, you can do more cycles, then the costs, let's say, per unit energy go down, and that's what you need. And finally, the link to industrial scalable and sustainable materials production, which is often forgotten in this field. So you can play with nice materials, but if they are scarce, if they are expensive, don't work with it. And this is for now.
Thank you very much. Okay. So yes, thank you very much for your presentations. Now we can start with the discussion and imagining a little bit the future of latent thermochemical storage technologies together. So I would like to start with the first question with you, Andrew. I mean, you mentioned 20,000 units already sold and a future of many more thousands and being sold in the next years. So what is your vision about the role of latent heat storage in the energy future of Europe and generally of the world? Do we target for having a latent storage in every building, or what would be your vision?
Good question. Yeah, I mean, I think any building with an independent energy system, meaning it's in the building only, is probably going to have a latent heat store. Or maybe a thermochemical store. I mean, you know, I love thermochemistry. I just can never get it to work. Let's be honest. We think that we've got to the point where we've cracked the problems of stability, price, affordable manufacture, scalability of raw materials. That means that in the next years, there will stop being a reason to make individual home water tanks. And there'll be every reason to make phase change material stores, either the way we make them or some other way. And, you know, from our side, we want to partner with people that will have plants that they will be shuttering and instead help them to make heat batteries. Let's be completely honest, we like partnership. So I think we see in that area, everything go PCM over 10 years. In other domains, probably not. I mean, you know, we've had some very compelling arguments for why interseasonal storage might well be a sensible means, and pit storages and so on. I think it's pretty challenging to go into using, for example, latent heat storage with those cost criteria, with that, you know, I mean, even over 100 years, you can't amortize the investment probably. But it's just a guess. None of us can see the future perfectly.
Oh, but that's a good saying. Like you see that water tanks could be substituted on a building level with latent heat storage units. Or this is a good vision, I think.
Close to 100%.
Unless
you need storage for the water, right?
Mhm.
If you actually want the water
Mhm.
as well as the thermal storage, you want the mass as well as the energy, then you'll keep using a water tank.
And I was also interested to see that you are expanding in China a lot. Do you see that the drivers in China are different than Europe? Do we have any lessons to learn from that, or would you say it's there are more similarities and differences?
So compactness of buildings,
Mhm.
that's true in China, right? And a lot of Europe. But there's another thing in China that's really interesting, which is people don't trust stored water. They like instantaneously heated water. And so actually there's a real advantage to anything that stores the heat in a different way and then drives the heat out into continuously flowing fresh water. So yeah, there are differences.
Okay. Thank you very much. Alex, I would like to continue with you. So a little bit along the same line. So where do you see the role of latent heat storage in our energy future, maybe specific from the Norway perspective and or the industrial perspective?
No, I see it as a good alternative to store energy when, you mentioned some numbers for how heating and cooling is important in the total energy use. Yeah, it's about 80% in the industry. So yeah, why storing electricity while you actually need heat or cold at the end somehow? And we see that to upscale something in a relatively sustainable way, then PCM is a good way to go. And the most sustainable would be to store in water if you need cooling anyway, and use it as a PCM, for example. But there are other PCM adapted to higher temperatures too. But we see it as a good solution that can upscale, at least for the industry.
I saw you had a very ambitious, or you mentioned some industries that you would like to have pilot plants in the next years. Are these partners that you already have agreements with, or is it your vision?
Oh, it's more than a vision. It's actual partners. Yeah.
Oh, they're
The goal for us is to start this spin-off company now in summer, and the 5 pilots that I mentioned, we are like already in agreement with the people to do that. So some of them are partners in research projects. Some of them are a bit less formally involved, but yeah, it's there. It's coming. Yeah.
Okay, so that's very interesting. One could say that industrial partners in sectors that used to be traditionally quite conservative or reluctant to implement new technologies are now starting to embrace latent heat storage. That's
no, it's a bit like the way research projects are funded somehow. It's hard to get private households partner in a research project, but the industry can somehow. So if you start this way somehow, you demonstrate, you can have some visibility into how things work. And we target kind of large scale as well. So for us is the perfect way to get out there, show what we can do, get the success story out, and then and go over mass production for, let's say, buildings, large buildings, commercial buildings, for example. So it's you always have to find out which is the quickest way to make a difference. And that would be ours. Yeah.
That's great. Thank you very much. So I would like to move to Elena again with a similar question, but now from the perspective of the high temperature industrial waste heat recovery and generally decarbonization, let's say. What is your dream about the role of latent heat storage, or where do you see latent heat storage playing a role in the decarbonization of high temperature industrial processes in the next 10 years?
Because I know now it has been published that energy intensive industry, so there are 4 main ones that those 4 is like steel, what was ammonia, ethylene, and what was the other? Cement. Those 4 account for 45% of the CO2 emissions of all the industry. And separated steel and cement, it's around 7% of the overall CO2 emission. So the goal of targeting those industries that we are doing now, it will help us latent heat or CPCMs to replicate in different industries around the world, because kind of there are similar processes, and that will boost the use of thermal energy storage. So I see that starting with these companies, and for example, in the UK, they are putting an effort on trying to decarbonize in industry, but specifically energy intensive one. Now, this project was funded also by UK in that framework. So it's how I see that it's industry and policies are pushing moving forward. Currently, we see that industries are coming to university in our center because they foresee the future, that they really need to reduce the energy consumption. And they are now willing to move forward to that. And they see together with the policy that they're helping with these technologies. I see now a movement that could really help. And I have to say it's needed. It's needed because companies, they cannot depend on foreign instability issues that we are currently facing.
So on your estimation, when we will see the first high temperature latent heat storage in industrial setting, or specifically for your technology, or generally, or what is your dream based on that?
Now we have another project that we are, because that project was for small scale.
Mm-hmm.
That in my case, small scale, I moved from milligrams to tons. It's a huge step, but now we are targeting bigger companies with more energy waste heat that they have.
And you have a partner who is commercializing this technology?
No.
Okay.
Well, I don't know. I think that on that sense, we are a little bit behind.
So maybe the big next step now
Yes.
is really to go for the commercialization with the industrial partner. Very interesting. And then I would like to also ask you the equivalent question about thermochemical storage. So what is your dream about the next 30 years, and where do you see the role of thermochemical, maybe also touching a little bit on what we said about latent? Do you see a similar role? Do you see a different role? And also maybe a bit the long-term aspect that you you mentioned.
Yeah, maybe you can start to answer this question with a thing, something which is going on now in the Netherlands. We have this heat networks, and they are closely connected to the large industrial areas. So basically, if you go to the harbor of Rotterdam or a few other players, there you have I think, developed heat networks. What you see, let's say, in the house, a large part of the housing stock is too far away from that. And the question is now, how can you transfer then the heat to, let's say, to that homes without building a heat network? One of the ideas which is now on the table and is really investigated with several big partners is to do that via thermochemicals and load them, let's say, at, industrial site, and bring them to a block level and have there a local heat network. That's completely different than the original idea, which was when I started was very simplistic. At least I had a very simplistic idea. You have a home, then you have a heat battery, and you are fully independent of the world. And I think I think that's not really the road to go. So I see it in this way. So and for me, this is, let's say, something in 10 years from now, you hope that this is really getting really mature. Let's put it like this, because there are also a lot of technological things still to be solved on the road there. Yeah.
Okay. And what about the long-term aspect? I mean, you mentioned an indefinite storage period. We talked also yesterday a little bit about the seasonal aspects. Do you see thermochemical storage as how do you see in which period?
Yeah, I think the ideal period, you can debate a lot about that. Of course, it should not be short, because then you always lose from water, for sure, because that's the most simple technology you have. So somewhere, let's say, in the order of, let's say, weeks, months, towards a year. But the only point is that if you go to seasonal thing, then the amount of cycles you make is relatively low. And then the cost, let's say per cycle, is very high. And then, yeah, in terms of materials cost, system costs, that might not be the road to go. No.
Okay.
So I'm thinking more, let's say, in the intermediate periods, let's say a few weeks, months, to cover, let's say, gaps in availability of renewable resources. But that's my personal view.
Thank you, Henk. So I would like to move a little bit to the audience questions. So the pre-selected questions is the ones I see. So to Elena, with CPCM material, do you believe will be the first in commercial applications? What CPCM material do you believe will be the first in commercial?
That's an interesting question. I think with the I mentioned before, we should target the working temperature ranges. So in our case, if we target for energy intensive industries, the painful path of moving from lab scale to industry, we did it. We learned, we know how to make it cheaper now, because it was kind of expensive from all this trial and error. And so the CPCM. So at the end, CPCM, it's going to be a matrix, so that it's going to encapsulate our PCM. In that case, I think I see molten salt nitrates, one of the, I hope it's one of the first ones to move to industry, because then that technology, we made it in a kind of modular way, so we can adjust the number of tanks to what it's needed, the amount of energy to be captured and reuse it. So, and nitrosols, I think it's going to be one of the first one, because it's there. We have proved it works, and now we need to convince it to replicate in different industries.
Okay, thank you very much. And the next question to Alexis: how large is the volume of the storage?
That was a little bit over 5 cubic meter.
Okay.
So
That was
a
clear
clear
question. We move to the next one to Andrew. What is the current state of possible temperature ranges and power? Is it already suitable for industrial high temperature applications?
So internally, we have minus 30 Celsius to 118 Celsius PCMs with multiple steps on that road, fully developed and ready to deploy. A lot of focus has been towards perfecting temperatures actually a little bit below the sodium acetate 58 Celsius to match up with high COP for heat pumps. So we've been focusing down on getting efficiency, getting performance, and getting compatibility with heat pumps. In David's development and the developments we do with the University of Edinburgh, we're pushing down to sort of minus 80 and up as high today as sort of 500 Celsius or so. But these are quite a long way away from being ready for market. You know, they're maybe multiple cycles of development away. Maybe some of them won't pan out. Maybe some of them are brilliant. So, you know, they represent the longer roadmap over those 10 years. And like everybody else, I think we're interested in targeting where the applications are. And sometimes that doesn't match. I mean, we all know this. Sometimes it doesn't match up well. You know, you've got a great material at X degrees Celsius, and the application is at, you know, X plus 10, and it doesn't match. And however hard you try, you just can't make it work. Or X minus 10. I mean, so, you know, it's tough. I mean, you would ideally just like to have a pallet you could go and buy. And we thought we would. I mean, early doors, we just thought we'd go and buy PCMs from other people. It didn't pan out, so we had to develop our own. But we're still in the market. Okay. Still in the market.
So great. Next question.
Oh, sorry, there was a power question. Let me just answer that very quickly. Because we focused first on residential hot water, which is actually relatively a very high power service. Okay, it's kilowatts per kilowatt hour is approximately 5 to 10. Yeah, you need 40 kilowatts out of your 4 kilowatt hour store in our smallest product. And that means we are very focused on very high power. And actually for us, as often as not, it's backing away from that for industrial applications, for district heating connections and so on, and working out how to be more cost effective, how to have less heat exchange surface is actually for us the challenge. But the good thing is we already scaled a high peak, so we can come down to some lower ones, we think.
Great, thank you very much. So the next question is about Alexis. What is the base component of the BOPCM? Is it sustainable?
That's a good question. So we got asked this quite often. In that case of the demonstration, the PCM was coming from Latent, and then we got the certificate, and we also asked the question, of course. And it's mostly vegetable oil, and part of it is from palm oil that was left behind after the food industry literally doesn't buy it anymore under the pressure of the customers.
Okay.
It's a lot of fields that are just left behind to rot. So in that way, for the quantity that is needed today, it's much more than enough available somehow.
Okay.
They are just not reconverted to something else.
Yes. Okay, so maybe now we can continue a little bit to the hard question of if we want to try to make some plans for the future. What are the priorities that we should set as a community to really achieve the visions that we set? So what are the barriers and what are the next steps we should plan? Yes. So maybe I can start with Andrew asking you that question.
Yeah. So, I mean, we obviously talk to investors quite a lot, and often they get out their calculators and their spreadsheets and they do techno-economic analysis, you know, from a perspective of a buyer. But the reality is most buyers don't do that, right? They actually buy things because they like them. They buy them because they're cost effective. They buy them because they've got low capex at the beginning, often. So I think from our perspective, it's about making the offer really attractive emotionally. You know, it satisfies the needs at the top of Maslow's pyramid. You know, it's about self-actualization. You know, I'm doing my part. And at the same time, honestly, you got to crush the cost out of it. And you've got to therefore be able to meet the buying price, whatever that is. And if you do those two things, it's probably going to work. That's where we're at. That's what we do.
Okay. So you see one major barrier or major opportunity is getting access to the people who actually have to buy or have to sell.
Yeah, I mean, you've got to do marketing, right?
Yeah.
I mean, a lot of it. And you've got to have a lot of partners who are talking to the buyers.
Yes.
Otherwise, you're not there. But you also have to get the cost right.
Yeah.
Honestly, if the cost isn't right, if all of us are working on things that are going to be 3 times, 4 times, 5 times the cost of some alternative, we're not getting there. Right? If you're 1.1, 1.2, 1.3 times, you might get there. If you're 0.7 times, you're there. We're not quite there yet, but we're heading there.
Very nice. Any other important points, or do you have any strong feelings about what is the most important thing we have to think about as a community for the next steps to yes?
Yeah, I mean, that's something that probably Sanamp has done, is to standardize the product, you know, to decomplex the whole thing, make it a lot easier to comprehend. I always think of the example of the heat pump. You know, most people don't really understand how a heat pump is working, yet they would buy it because they understand the benefit for them, you know. And they would not calculate how many years it would take for them to pay it back, but they understand it's a good thing and they just buy it without the need of understanding. And I think if we at least get there, you know, that's going to be a much easier step than to enter the common products that people think of when they are buying stuff. Yeah. But the industry is the same. Like it's a thermal system after all, so it's complicated. There's like temperature range. There is the power output, the power input, where you get the heat from, and so on and so on. So it takes a whole lot of case study, development, engineering, and so on. But when you come with a product that is a bit more standard, then these steps are much shorter. And it's all about price and availability, what's available today. So if you shorten these steps there, your availability is much easier.
Thank you. Also wanted to say something?
Yeah, I think if you go to the thermochemical field, which is much lower TRL level, if I think what we should do there is making things more flexible. First on the material level, so basically everything is really hard, let's say wired at the moment in, let's say, the phase behavior of material. By the way, that's also for latent. So where we can create flexibility there, that well helps a lot, because then you don't have to develop over and over and select new materials for applications, but then you can work on, let's say, a platform. That's one. On the system level, you have a similar thing. So you would like to separate as much as possible your storage, heat exchanger, and the point where you get reaction. And that's one of the major challenges, because then you can do with, let's say, small heat exchangers, small reaction units, but large storages, which makes the system far more modular and flexible. And especially for the TCM community, that's also what you already realize, is I think this cross-fertilization with people, we really think about the first, let's say, real business cases. That's because I think there's still a lot of work to gain and clarity also for the research community. So that's more an invitation from people who are really looking more to the business cases. Yeah.
So we heard about knowledge transfer, we've heard about interdisciplinarity, cross-fertilization. Maybe, Elena, one difficult question. I mean, how do we achieve that as a community? We have a stronger collaboration the next year, that we really achieve this knowledge transfer, this working together to achieve our common vision, let's say. Do you have any concrete plans? How you plan to work more interdisciplinarily?
I think it's a little bit what Andrew said, share and communicate, not only among our research community, but also just to think about on the social aspect. Now consumers are more aware or more concerned where energy comes, how whatever they are buying, they start talking about the CO2 footprint. And they are, I've seen it today, this morning in one advertisement, coming from the bus, that it's first time I see selling milk talking about CO2 emissions. So I think we need to bring all of us towards one target, that it is decarbonize all our energy system. And I think this social aspect, it will play a key role, because at the end, what we want is people to use it. And they need to know about what they want to use, but also the benefits, and we need to tell them. And so in a easy way.
Okay, thank you very much. Maybe we have time for one more question from the audience. To Henk, on material level, what is the targeted price per energy unit to make it competitive on the market? That's a wonderful question. So which TCMs are in the focus at the moment? So that's maybe more.
Yeah, maybe you can answer a bit differently. So this is kind of political way to answer a question. So where we are now, I think on the material level, you can think about, let's say, 4,000 euros per, let's say, gigajoule, if you can recalculate that in something. Then you have a bit of idea where we are now. So, and the costs, let's say you have thermochemical, the thermochemical systems, I think is exceeding that. So for me, the most critical thing is at the moment, not really in lowering the materials cost, but more in lowering the system cost first, because that is limiting basically the cost now. It doesn't give an answer to the numbers. I don't have a number.
Okay, great. Thank you. And then maybe the last question, that I find that an interesting one, how are environmental aspects, manufacturing, energy sustainability, etc., in the production, use, and end of the life taken into account? I mean, we saw you choose to go the bio-based road, even though it's not the cheapest, maybe at the moment, right? So for you, sustainability, or you saw that there is a need for sustainability personal, or I don't know, maybe you can say something about it. And Andrew, we were also discussing yesterday about your also wish to make your materials more sustainable. So maybe you can give me.
Yeah, I can start. Yeah, so the bio-based was definitely the motivation at the beginning, like to use bio-based PCM. It's like one of the main components in the solution there. After that, there's of course the heat exchanger itself, a lot of metal, a lot of stainless steel. And then we are looking now at how to source the stainless steel on more sustainable ways, eventually look for alternative materials, maybe aluminum, things like that. And then you can source it in a much more environment-friendly way, let's say. It can never really be zero, but then you can calculate on the total lifetime somehow how much CO2 you're gonna save through the use of that storage too. And I think that could more than complement then. Another thing is the end of life is quite important. So if you manage to have some kind of simple construction that is not mixing too many elements together in a way that you can never separate them again, then you can recirculate them. And that's what we also focus on. So that's the solution has a value at the end of life. And of course, that's to have a long life. So that's something we focus on very much.
Thank you very much, Andrew. Do you have something to?
Completely agree on the circularity point. It's actually a real advantage in this field over the electric battery world. The electric battery world is really hard to separate everything. You know, think about recycling a lithium-ion battery with all its separators and membranes and so on. That's hard. So I think that's an advantage in this field, actually, that we can have a better story there. I'm going to summarize this very briefly. We committed at COP26 to the SME Hub process. We appointed a net zero analyst, and we are working our way down the curve as fast as we can. What we're really good on is Scope 1 emissions, because we manufacture in an electrically driven factory in Scotland, which has an extremely low carbon intensity in its electricity. So we kind of lucked out there. We already got, to a really good Scope 1 emissions. And we're working really hard on our Scope 2 and Scope 3 emissions. We ultimately, vision-wise, maybe in 10 years, we have a vertically integrated manufacturing that takes, biomass and renewable electricity in on one side, along with some metals, and on the other side come out products with the absolute minimum metal content that are potentially carbon negative if we play our cards really right. That's going to be hard, but maybe we can get there. That would be ideal.
Okay, so very inspiring vision for the end. So I would like to close our session now. Maybe we can try to summarize some of the important points, mostly looking in the future. I heard from all of you need for education of different stakeholders, actually, knowledge transfer and interdisciplinary work. Also, we start talking about emotions, communicating the importance also on an emotional level, or the making things standardized so that it's also easier for the people to make the decision to purchase it. We should work on sustainability on all levels, and maybe to separate a little bit thermochemical storage from the latent heat storage. Maybe for thermochemical, we are working more on the material level with the goal of having stable materials for a pilot plant in 10 years, or for commercialization even in 10 years. And for latent heat storage, we have a lot of solutions that are now ready to go to the market. So we should work on making the stakeholders ready to accept these products while working on new materials and new products for different applications on the way. And continuing to work together as a community, even in a stronger way and more interdisciplinary. So thank you very much. Thank you, everybody. I think now